Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capella High School, and I want to welcome you to this lesson on scatterplots, correlation, and regression lines. So let's start out with the scatterplot. Here I have a scatterplot, and for each data point has an x-coordinate and a y-coordinate. So sometimes we call this bivariate data or paired data. I would describe this scatterplot as having a positive association because the direction is positive. It goes from lower left to upper right. So a scatterplot shows the relationship between two quantitative variables for the same observation. We call this bivariate data or sometimes paired data. Each observation in the data appears as a point in the plot fixed by the values of both variables in that observation. An explanatory variable is a variable whose values are used to explain or predict corresponding values for the response variable. A response variable is the measured outcome of a study. If you have one variable that is clearly the explanatory or the independent variable, and the other that is clearly the dependent or response variable, I always put the explanatory or independent variable on the x-axis, the horizontal axis. If you don't have a clear independent and dependent variable relationship, then either variable can go on the horizontal axis. So let's talk about the direction of an association. A positive association means that as the values of one variable increase, the values of the other variable tend to increase as well, or the values increase on average. Two variables are positively associated when the scatterplot moves upward from left to right. A negative association means that as the values of one variable increase, the values of the other variable tend to decrease. Two variables are negatively associated with when the scatterplot moves downward from left to right. So what's an example of two variables that have a positive association? Suppose I have the data on many students at Capella High School. I know their GPA and their SAT. When I plot that, I would expect to see that as GPA increases, SAT also tends to increase. So the plot would move upward from left to right. What variables have a negative association? Well, study time and test errors. As study time increases, the number of test errors would tend to decrease. So these would have a negative association. If there is a strong positive relationship between two variables, we would expect that most of the observations that were above the mean in one variable would be above the mean in the other, and vice versa. In this graph, I've drawn the horizontal and vertical lines to approximate the mean weight and height. Notice that most of the observations are in the upper right and lower left quadrants. Only a few observations break this pattern. So here's a graph showing a positive association or positive correlation, and another one showing a negative correlation. Another way of describing scatterplots is to discuss the strength of the relationship. The strength of a relationship in a scatterplot is determined by how closely the points are to a straight line. The closer the points are, the stronger the relationship. So here in the first upper left, I have a strong positive relationship because the points are close to the line. In the middle, I have a moderate positive correlation, and in the very right, upper right, I have no correlation. Scatterplots take on many shapes, so that now we're going to also talk about describing scatterplots in terms of their shape. So here on the left, I have a linear correlation. A linear relation means that the points tend to follow a straight line. As the x variable increases by 1 unit, the y variable tends to change by a constant amount on average. And on the right there, I have I definitely have a relationship between my data points, but it is not a linear relationship. It is a semicircle. So when you are describing a scatterplot, I want you to discuss each of these characteristics. I want you to talk about the direction. Is it positive or negative? Then talk about the strengths. Is it strong, moderate, weak, or no association? Then talk about the form, and here your choices are basically linear or non-linear. And finally, discuss whether there are any unusual features such as outliers, clusters, or deviations from the pattern. So that is how I want you to describe a scatter plot. Now let's talk about the correlation coefficient R. This is a measure of the strength and direction of the association between the two variables. It is also called the Pearson's correlation, and it is abbreviated for the sample correlation. It is abbreviated with the lowercase letter r. Population correlations are represented by the Greek letter rho. The correlation coefficient R has no units. It is a unitless statistic. Correlation coefficients R can range between -1 and +1. So if you see a correlation coefficient greater than 1, you know something went wrong. An R greater than 0 means that you have a positive relationship. That is, one variable tends to increase as the other increases. An R less than 0 means that you have a negative relationship. That is, one variable tends to decrease as the other increases. If the correlation is close to 1, +1, that means you have a strong positive relationship, but not necessarily a linear relationship. However, if R is equal to 1, the variables have a perfect linear relationship. If the correlation coefficient is close to -1, that means you have a strong negative relationship, but not necessarily a linear relationship. If R is equal to -1, the variables have a perfect linear relationship. A correlation close to 1 or -1 does not necessarily mean that the relationship is linear. I can draw a curved pattern that has a correlation close to 1 or -1. If there is no relationship between the variables, such as a random assortment of data, the correlation coefficient is 0. However, the converse is not true. So for example, I could have a correlation coefficient of 0, let's say my data, and by having my data in a circle, let me just put my data in a circle, that would give me a correlation coefficient of 0. Okay, so the correlation coefficient is 0, but there is a relationship between the variables. It is a circular relationship. Here is our formula for the correlation coefficient. Now this formula is on the AP exam, on the formula sheet, but you will never need to calculate it by hand. Your calculator will always do this for you. This is the correlation coefficient for a sample. Now, a couple things that I want you to note. The correlation is based on z-scores, so units don't matter. What I mean by that? So here is the correlation coefficient for the x-coordinate, and excuse me, here is the z-score for the x-coordinate, and here's the z-score for the y-coordinate. So that's why I write here the correlation is the average product of standardized values, z-scores. So correlation is based on z-scores, so units don't matter. The correlation between height and weight is exactly the same regardless of the units of measurement. So I could be measuring height and weight by inches and pounds or centimeters and kilograms, and I'll get the exact same correlation coefficient. I put a pirate there just in case you want to have a talk like a pirate day. So here I've given you correlation coefficients and their data. So I just wanted you to look at some of these so you can get an idea of what correlation coefficients go along with what patterns. And here I have some more. These C's should actually be R. So a coefficient, an R of 0, would be a random scatter of data. And as you can see, as the absolute value of my correlation coefficient increases, the data gets closer and closer to a line. So as the correlation coefficient increases, the strength of the pattern increases. Okay, Although there is no hard and fast rules for assigning strength of an association to particular values, here are some general guidelines. If the absolute value of our correlation coefficient is less than 0.5, then that would be considered a weak correlation. If the absolute value of the correlation coefficient is between 0.5 and 0.8, then that would be classified as a moderate association or correlation. And if the correlation coefficient in absolute value is greater than 0.8, then that's a strong correlation. I also want to note here that sample size is important to determining correlation coefficient. So as your sample size increases, you tend to get higher correlation coefficients. Let's talk a little bit about correlation coefficients. Correlations describe linear relationships. They do not describe nonlinear. So correlation coefficient assumes linearity, but you can't use it to prove linearity. Correlations do not prove causation. So just because X and Y are strongly correlated does not mean that X causes Y. There might be a third variable causing a change in both variables. Also, we can't be sure which is the direction of that causality flows. Is causality flowing from X to Y or from Y to X? Correlation coefficient will not tell us that. Correlations are strongly affected by the presence of outliers. That is, correlations are not resistant to the influence of outliers. Use correlations with caution when there are outliers. Also, switching the order of the variables does not affect the correlation coefficient. So the correlation of XY is equal to the correlation of YX. And again, correlation does not change when we change the units of measurement of one or both variables because, of course, we are standardizing those variables in our formula. I want to talk briefly about a Simpson's paradox. This came up on the AP exam a few years ago. Simpson's paradox is a phenomenon in which probability and statistics in which a trend appears in several different groups of data but disappears or reverses when these groups are combined. So let's look at this data here. In this graph, we see that X and Y have a strong negative correlation when the points are black like that. However, once we stratify by some confounding variable Z, encoded by those colors, the correlation flips to a positive correlation within each strata. So that's the Simpson's paradox. There I have a negative correlation, now I have positive correlations. Remember this from algebra, y equals mx plus b, m was the slope of the line, the rise over run, b is the intercept with the y-axis, the point 0b. Well, I want to dazzle you with these fancy graphics right here. There's my y-intercept, there's my slope, rise over run. In algebra, we said that the slope m tells us how steep or flat the line is. In algebra, a slope of m equals 2 means that for every 1 unit change in x, we got a 2 unit change in y. Well, in statistics, we have to do things a little bit differently. Specifically, we have different notation. So we are going to write our linear regression equations like this. Y hat is equal to a plus bx. And x is the value of the independent variable, also called the explanatory variable. That's x. Y hat, and that's how you pronounce it, y hat, with a little hat on it, is the value of the dependent variable, also called the predicted or response variable. So whenever we have a predicted variable in regression, we're going to put a hat on it to indicate that. And here's our model. Model will be y hat is equal to a plus bx. A will be the y-intercept of the regression line when x is equal to 0. And b is the slope coefficient of the line. And here's how we're going to interpret b. It is the amount that the predicted y value changes when x increases by 1 unit. So when x increases by unit, the equation will have a predicted change in y equal to the slope coefficient, or the value of y will increase by b on average. Now, what we're going to learn in our next unit is that we will estimate a and b based on the data that we collect. Let's talk about extrapolation. This is not something I want you to do. I want you to be cautious of extrapolation. Extrapolation is predicting a response value using the value for the explanatory variable that is beyond the interval of the x values used to determine the regression line. Such prediction is risky because the results are potentially not accurate. So what am I talking about here? Extrapolation is using a regression line to make predictions outside of the sample. And we do not want to do that. So this one here reminds me to tell you that sometimes the intercept does not make sense, does not have a good meaning from the context of the problem. So whenever you are asked to interpret the intercept, always ask yourself, does this make statistical sense? So let's talk about this right here. The scatter plot on the right shows the number of miles driven in thousands and the advertising price in thousands of dollars for 11 used 2018 Toyota minivans. The regression line shown on the scatter plot is y equal to 27 minus 0.2x. I should have a y hat there. Y hat is equal to 27 minus 0.2x. So that's my regression line, and there's my scatter plot. We could ask you to describe the relationships displayed on the scatter plot. So you're going to have to talk about the direction, the strength, and the form, and whether there's any outliers. So here's my answer. The relationship between miles driven and advertised price appears to be linear, negative, and strong. Also, there do not appear to be any outliers. I call this a strong relationship because the data looks to be really close to the line. Then we can ask you to identify and interpret the slope and the y-intercept. So let's talk about the slope first. The slope coefficient from my equation is minus 0.2. So when mileage increases by 1,000 miles, the predicted price decreases by $200 on average. So the words predicted and on average I've highlighted because those are going to be important. Those are going to be part of the rubric. Now here I've used both, but I think you probably could get by with just one. But to be safe, I've included both here. So the predicted price decreases by $200, or the price decreases by $200 on average. That's what we'd be looking for. How about the y-intercept? The price intercept is A equals 27. That comes from my equation. When the mileage is 0, the predicted price of a used Toyota minivan is $27,000. And whenever you are asked to interpret the y-intercept, ask yourself, is this interpretation of the intercept statistically meaningful? And in this case, well, I do have data points that look pretty close to 0, so it does make sense to talk about this as being the predicted price when mileage is 0. Recapping, to understand a set of data, first thing I want you to do is start with a graph. That's always a good idea. Graph your data. If the data concerns the relationship between two quantitative variables, use a scatter plot. If the variables have an explanatory response relationship, be sure to put the explanatory variable on the horizontal axis. And finally, when you look at the scatter plot, describe the overall pattern by discussing its form, its direction, and its strength. Also describe any outliers, clusters, or other deviations from the pattern. And that's my presentation for today. Thank you very much.